did deal with a lot of this yesterday. We actually started on this. So slide 2 is just a starting point for us. I'm going to go ahead and pull that slide 2 up. So if I get you to move into the center for the conversation, to take notes to your future forgetful self about this. Okay.
Are you an 8 or a 9? You're an 8?
So,
Wait, you're an 8. Whose dad's are those then?
I need to find the unit. Does anybody have, hey guys, I need us to have our unit 4 Frere models out.
Well, you got it in there?
If you didn't already have them, then yes.
What was that? What was that?
Oh yes, you're right. I gave you all yours yesterday. It's my bad. Say again, Jamie.
She wanted to.
She won't help.
What I went ahead and gave you yours, but okay.
Oh, I ain't getting no pay.
Come on, yes you did. Okay. So ladies and gentlemen, let's build on what we talked about yesterday because I know we didn't get a chance to do some notes. So here is slide 2 of that second Desmos activity. And what is the very first question? It says what? What type of function is created by 3 linear factors, okay? So what type of function is created by
Cubic function.
Okay. Now, a lot of us are shouting out that 3 linear factors. By the way, don't ever forget, I keep using this word. What do we do with factors? Multiply, right? What transformation ties into the idea of multiplication? Dilation, right? So one way to talk about this is, let's say I just start with this line right here. Okay, I'm starting with this line right here. And then I'm dilating it by these 2 factors, right? I'm transforming it. Remember, this one line has how many zeros? That one line. This one line. That one line has how many zeros? 1. But when I dilate it by, let's say, this second line, I transform it by this second line, how many, and so I would point out, once I dilate it by the second line, what's a positive times a negative? Right, so I know that all these would be negative. What's a positive times a positive? And so I got to turn around and get back to 0, and what's a positive times a negative? Negative. Once I dilate it by a line, does it still only have 1 0? No. It now has 2 zeros. Remember, the whole idea of where it says dilating a function by an expression, does it stay the same type of function? No. So, in the top left up here, I want you to make sure you make notes about this. You did not get this yesterday because you weren't here, right? Was anyone else not here and not get this packet? Come on, you were here, dog. Preston, you were trying to troll everybody yesterday, the whole class, so I know you were here.
No, I wasn't.
Oh, wait, that's the paper we wrote our notes on? That's the paper we wrote our notes on? Okay. I thought it was something else.
So guys, we should be looking at page 1. Should I put it there? That's 5. Oh, okay. Mr. Robbie, they're over here.
Okay.
Amaya. Anybody else not here yesterday who hasn't gotten his packet yet?
On the right. Nope.
Alright, I already gave it to you. Alright, everyone else is here, I think. Staples are on the back shelf, or back book case. Alright. So, y'all, top left. dilating a function by an expression. What is that doing? Okay, it is multiplying, right? So when we say dilating by an expression, top left, where it talks about dilating by an expression. First things first, we want to recognize algebraically that means we multiply. Okay, so we multiply, ooh, I do like that note, the outputs. But more importantly, what I want to make sure we understand clearly is when we dilate by an expression, what is it doing? It's transforming the function how?
You said what?
When we dilate by an expression, remember, I started with this purple line right here, right?
Yes.
Okay? But then I dilated it by this green line, and I created what type of function right here?
A quadratic.
We created a quadratic, a parabola, right? So we multiplied those outputs, we dilated by an expression, but we transformed the original function by what? What happened when we went from a linear to a quadratic? How did that transform the function? Okay, there's something with that though. Say that again. I need you all to remember and pay attention to this. When I dilate by a linear function, I'm creating a new what? A new zero. So by creating new zeros, that is critical to understand that we are creating new zeros when we dilate by a function. Because, well, I'll show that in a second. We're creating new zeros. Top left, dilating by an expression. Right? Okay, remember this is what we explored and we found yesterday. This is not me just straight up telling you. This is what we saw happening. We created new zeros, and remember, what does that do to the degree of our function?
Change.
But how does it change it? And
So we added it on to what you said?
yes. So by creating new zeros, and what is that doing to the degree of my function when we add new, create new zeros?
Making you point.
No, the one I just gave you. That one, right there.
Wait, what was your question?
So when we create new zeros, what does that do to the degree of the function? Let's remember this really quickly, right over here.
Making a y.
Y equals mx plus b. What degree is that?
Linear.
What degree is it?
Adding.
It's degree 1,
Yeah.
because it's x to the first. Quadratic, y equals ax squared plus bx plus c. What degree is that? So what's happening to the degree when we create those new zeros?
Third degree.
It increases.
Yeah, period. Yeah.
Okay? So the degree increases, and it's not random. If I create one new zero, how much does my degree increase by? By 1. If I create 2 new zeros, how much does my degree increase by? Why is that? Yeah, but there's a 3-word thing that we've talked about. It's pretty fundamental to algebra that connects the degree to the number of roots. So, guys, it's still on board. Pause for a second. I need us to hear this. The reason why, if I create 1 new zero, that degree increases by 1. And when I create 2 new zeros, the degree increases by 2, is because of this 3-word thing, kind of 4 words, that is pretty fundamental to algebra that connects the degree to the number of zeros or roots.
we're going right to that part right there.
We already talked about it.
Multiplying.
Let's go with.
Multiplying.
And you want to put that, everything to red on the top left?
It is of algebra.
Factor. That'll add algebra. Feels like we're level 1.
Fundamental theorem about it.
Good, that one you doing.
Forgot about that. Fundamental theorem of algebra. I'll show you the proper definition soon, but in the plainest terms, whatever the degree is, and whatever the degree of a polynomial is,
We write that.
I would write this,
Under it.
well, you could write it at the bottom, maybe on the back. I would probably do the zeros. I would put it somewhere under the zeros of a polynomial. No. No, stay calm, stay calm. Either, so the back side is completely blank, you can make notes there, or I would probably put it in the bottom half of dilating a function by an expression. Because we are going to build on this.
Right that, there too, top left.
Nukari, I love you, but I just answered that question.
And I was writing, I was,
So when I'm talking, pause for a second and listen.
yes, sir.
Hold on.
I think you're right at the back of the bottom box, I heard.
So, fundamental theorem of algebra. Whatever the degree of a polynomial is, that's how many roots the function has.
Yes.
Hey,
Okay?
wrong. R, okay.
Someone apparently needs to put their phone
Can we
up.
write it? That was Mr. Harvey.
That's my bad.
That was Mr.
Oh,
Harvey.
That was me.
my bad.
No, it's my bad. Yeah, you know what? You're right. Yeah, you're right.
Say again. So, remember I was saying, we're gonna use this in the top left, so I'd probably maybe put it in the bottom half of that top left side. Okay? Smooth, Dewan. Did you not see the food coming out of your mouth? Did you not feel that?
Oh, no, whatever. My fault.
So, here's the thing. We can clearly see it. A linear function has how many zeros?
What am I tweaking?
One single line has how many zeros? No, it's the first Wednesday of the month.
That's what that was. That's what that was.
They're
They
checking
did
the
say
alarm.
something about starting at first.
Hey, see,
I thought that was true.
Hey, one, I will never, ever tell a student who I voted for, but two, let's try to learn math. Like, over the last week, pause, over the last week, we have been less focused than normal. So, I need us to focus and engage. There's a handful of us that have been on it, but Preston, no more trolling people in the middle of class, no more side conversations during whole class discussion. We're focused in learning and asking questions when we have them. Taj, what's your question? So, the degree tells us how many roots there are, which also means however many roots there are, that's the degree. So notice what Taj is asking, like this definition right here tells us this. Whatever the degree of a polynomial is, that's how many roots the function has, okay? But that also means if the function has 5 roots, what degree would it be? So 5th degree,
Yeah.
right? So whatever the degree is, that's how many roots it's going to have. That also means however many roots it has, that's what the degree will be. Yes, Jamie?
Did you upload the video from yesterday?
No, I completely forgot to convert it, but I've converted this morning and so I uploaded it. Same thing we started working on Monday. So stay calm, we're going to continue working on it. Now,
You can tell me this.
Okay.
I've been lost.
so,
just catch.
one thing I'm going to point out really quickly. What does the prefix poly mean? Poly just means,
Probably just be anything.
poly means more than one, many, right? Poly means more than one.
I ain't say that.
What does nomial make you think about? Numbers, right? So, it's a little bit beyond just many numbers, but if you break it down, there's that. So, let me do this really quickly. So, sit over there. Do you see me writing, dude? Okay.
Can you find out the number for the code? You can take it and find it.
What you did?
Okay. So, pause for a second. This is what I'm talking about. When I say pause for a second, we stop, we pay attention, we don't get distracted. So, what I've done, what we've been working on, this idea of multiplying linear factors, the idea of multiplying other types of factors, that's the foundation for what a polynomial is. But I'm going to give you this as a starting point right now so that I want you to think about what is the pattern that you see. So what is the pattern you see here in the examples of polynomial functions? And what are these non-examples here? So this is just from an algebraic perspective, but there's a pattern to what makes those polynomials polynomials. Let me add actually one more in there. Those are some examples of polynomials. Sorry, I'm just going to add. Well, I want to make sure that we build a strong understanding here. So we've got examples of polynomials here, and then these are not polynomials. I want you to come up with a conjecture, a prediction of what you think makes a polynomial, and what makes things not polynomials. I want you all to talk about it as a small group for 2 to 3 minutes. We're going to come back together and come up with a proper definition, algebraically at least. So, write your predictions down for what a polynomial is on the back side of this sheet. Thank you. Thank you. Thank you. All right, so I'm going to start with a prediction that I just got that I want us to build on and think about. So the prediction was Cameron. So Cameron, what'd you say? It's the set of variables and coefficients, right? So that's a good starting point. One thing I will add on is I will say this. It's the set of terms with variables and coefficients. That's a good starting point. Now, here's what I want to build on with this. So first off, how many terms does f of x have here? 3 terms, okay? How many terms does y equals 2x minus 7 have?
1.
2 terms are separated by addition and subtraction. So that's 2 terms, okay? But here's what I want you now to think about. First off, when I look at all my examples, when I come up with a conjecture, that definition needs to fit the examples, and then the non-examples don't have that. So, do all of my examples have variables with coefficients?
No.
Which one doesn't?
The what?
Y equals?
No.
I got a variable right here. Does it have a coefficient?
So, what set of those ones?
Say, with these do too? Some of them do. So first off, and this is what we want to build on.
Let me answer. This is getting class.
Hello? Yes. No problem. Kamaya, Miss Hall wants to talk to you about something.
Oh man, she was talking to me.
Hey, right here. So, first off, and so, Preston, I want you to hold on to that idea, but my only question right now is, looking at my examples, are they all terms with variables and coefficients? And I will say this, it's okay to have a constant, right? This might sound weird. Really, Preston? What just happened? Can you pick it up and throw it away? He broke the pencil. I heard it crack. All right. So a constant, hey, right here, guys. A constant can be written. I wouldn't ever write it this way, but it can be written with x to the 0. Because what is anything to the 0 power? 1. So be careful. Remember, it is 1. And so 7 times 1 would just be 7. So even these constants have variables, right, with exponents. And so do all of these, are these terms with variables and coefficients? Yeah. Yeah. Okay. They all have terms that have coefficients. Even if I write x squared, what would the coefficient for x squared be? 1, right? It's 1. So that would still fit in. But Preston, push back on what you just said. Or talk about what you just said.
What?
No, before that, with the issue that you had with that definition.
I don't know what I said. I think I got short-term memory loss.
Okay, so
From you.
here's what I now want you to think about. Listen, all of this fits for the examples. But when I look at my non-examples, are there some of these non-examples that have variables and coefficients? Which examples? G of x has a variable and a coefficient, right? Understood 1. Y equals, that has a variable and a coefficient. So, notice those two are breaking this definition, right? Because this definition needs to be true for all my examples and not my non-examples. So I want us to think about how can I refine this to account for the fact that g of x and y here are not polynomials. So what do we need to change about that definition so that we would not be including g of x and y equals, right? So what is the issue here, and how can I change the definition to fit that? So let's take 2 more minutes, talk to your group to see what would I need to change about that definition to make it work for all polynomials and nothing else. What do we need to do? Talk to your groups.
He just told you what we needed.
I think he's talking about what do we need to do to change that definition.
Oh, don't have anything.
Well, let's think about it, Preston.
Very top. Person's at that. Oh, I didn't think it.
So,
So currently we have set of terms, no present coefficient. You want to actually modify it.
So I'll point this out. So what's the issue with g of x and y? Is it the coefficients or is it the variable side? It's the variable side. Okay. So what's the issue with g of x and y when it comes to the variables? Why do g of x and y not work? Because wherever it doesn't work, that's how
I'm in there.
So think about those variables. Think about those. Surface. It might be somewhere there.
What is weird about the non-example?
Keep talking about that. Keep talking about that.
Okay, interesting. Something to do with the exponents, I like that. So how can we, what's the modify our definition up there to account for those weird? Mr. Hopkins.
Okay, but I want you to look at that next. Is that
Okay. Positive exponents, well, that 1/3 is positive, right? So I like that. Keep testing, keep thinking about it.
How would you
Okay, no more throwing in this general area, no matter who or what or when. No more throwing.
So continue thinking about any predictions?
Good one. Thank you. What are we thinking here? How do we want to modify our? Thank you. God bless you. The one. Be sure everything agrees. Be sure everything agrees. How can we modify the definition? What are we thinking here? The idea is how we can modify this definition?
That 1/3 is positive.
So we already have variables mentioned up there, right?
There's one more.
Do you want to change anything about it?
Not just positive variables.
What do you want to change about the coefficients?
Change x squared to 1.
So a good strategy is think to yourself, those non-examples,
Did I see a hand up over here?
what are weird about those that's different from all those actual examples?
Is it the variable that's on
They don't have it.
Yeah, right, so g of x and y, they have coefficients.
What did bounce that?
But what about those non-examples are weird compared to all those other examples? Think to yourself.
Thank you. Thank you. Okay. So, I'm gonna have Addison add in some information in a second. Yes. Okay. If we don't see it anywhere else, I need to bring this information out because Addison has something to add in. So hold on, Addison, with what you talked about. Over here, I didn't get to talk to these groups very much. What did we see that we can change about this definition so that it only works for these polynomials and not for these?
It's on
I
the
didn't,
whole
I
number
didn't,
of
I,
exponents.
I didn't really see anything, but I thought on it. I thought about it. But I
Okay.
didn't see
I think we should change
So,
that
Jay
to
Mike.
once.
What were you saying?
I said it's on the whole number of exponents.
Whole number exponents.
3/8 has a whole number.
What do we mean by whole numbers?
Oh, I mean,
Like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13.
Not necessarily just, so remember, 1, 2, 3, 4, 5, that's the natural numbers.
Yeah,
What does it start with? 0. Remember how we said
Oh,
next to the
yeah.
0 right here?
So I think it's only natural numbers.
What? We just said that there is an understood x to the 0.
Oh, I see
We
that.
would never write it, but it is,
What?
what, say it again, J. Mike?
Well, what I said.
I don't know, what did you
All
say?
numbers.
Whole number what?
exponent.
Yeah, whole
Exponents.
number.
So remember how you were talking about the whole variables? Whole number variables? It's not the variables, it's the what?
Exponent.
Look at all of these exponents.
Well, are you asking about degrees?
Well, kind of. Hold on a second.
Just kidding.
Okay, hey, can I finish?
Yes, sir.
Okay, thank you. So, look at all these exponents. What kind of numbers are all of these exponents? Whole numbers, right?
Yes.
When I look over here, are all of these exponent whole numbers?
No.
So,
Not at all.
how do we change this definition? These are functions with
Variables.
terms. Alright, so I'm going to use a fancy-ish word, but it's just such that. So the terms such that what? What do those terms have to have?
Whole number.
What are the whole numbers?
Exponents.
The exponent. So a variable, what are we going to call this right here that's at the bottom of the exponent?
Coefficient.
Not the coefficient. Remember, the coefficient's out in front. So say
Is that
No,
not
so.
that. Hey guys, what do we call the thing here that's at the bottom of a power?
Ain't it?
There's a something to
Oh,
the
coefficient.
exponent, starts with a B.
Base?
Base, there we go. So, with terms such that the base is a variable, and the exponent is what kind of number? It's a whole number.
That's a lot of words.
Oh my gosh, dude. Everything's a lot to
It's
you.
not even a complaint, man.
Okay, it's just a statement.
Yes.
So, Cameron, phenomenal notice of its terms with variables and coefficients, right? The only thing, and so I use fancier language with it, but the only thing we really have to notice and change is that it's a variable base, right? And the exponent is always a whole number. That's it. So all of our polynomial functions, algebraically, there's more to it than just that we're going to go deeper into. But algebraically, this is what I would have on the back with my examples, my non-examples, is that my polynomials are functions, right, with terms such that the base is a variable and the exponent is a whole number. And are there coefficients? Yes. It definitely also has coefficients. But the priority is a variable base to a whole number exponent.
Ooh.
Got that down? Right? Variable bases with whole number exponents. variable bases with whole number exponents.
And the exponents is the whole number exponent.
Whole number exponents. Or exponents that are whole numbers.
Oh, and the exponent is a whole number.
The exponent has to be a whole number, yes sir. Now,
I'm not the last thing is
when we come back, excuse me, hey, right here. When we come back from lunch, what we're going to do is look at how we construct these polynomials, okay? That goes back to the factors, and so we're going to go deeper into those factors. Those are polynomials.
Caviar all in my bed.
What is that? Of x not a function. It helps if you turn it this way so it can see.
Oh, my bad. You mean zoom in?
Okay, so what's not, what is, so, there's something else here that, what's the issue, I guess?
the -7.
No,
It has no,
f of x.
it has no coefficient. It has no coefficient.
It doesn't really, well, I mean, everything always technically has a coefficient of 1.
What you said, what was the question? What was the question?
Hold on a second, we focus? Okay, like,
Let me get one.
I have ears.
Mr. Kenny just let
I will get back from Mars.
Mr. Kenny let that throw it up without pencil.
He was already gone by the time I found out, Juan. Hey, chill.
So what you gonna do?
So
He's in my 4th block. I will get it.
Go back.
I will be in here. I'm not going to take my
You're recording?
Guys, I need us to focus on trying to learn something. Why is f of x not a polynomial?
Jen, you keep this? I got you.
Technically, there's always an exponent.
You keep the joke too.
Guys, what is there that violates this rule? Thank you.
I said that.
Guys, that square root. That, like, we need to be more clear. It's not just that it's not a whole number exponent, like that square root makes it not a polynomial.
I said it. Mr. Kenny.
Okay? G of x, what's the issue with G of x?
It's not a what for it's not a whole number.
So, what is that exponent? It is 1/3, which is not a whole number. There we go. What's the issue with h of x?
It's no matter.
It's a whole different which one.
It's in what you call it. It's in.
Sine function.
It's not.
So, that sine, right, is not an integer or a whole number exponent. What's the issue with y equals here?
No whole number exponent.
That exponent of a -2, right? That's an integer, but it's not a whole number. What's the issue with k of x?
No whole number.
The fraction, and be careful of that fraction. When we say fraction, what's that fraction bar mean? Dividing by. So we're dividing by x squared, right? We need to multiply by x squared. It needs to just be an x squared. So, functions with terms such that the base is a variable and the exponent is a whole number. That's what makes a polynomial a polynomial. Okay? Now, when we are, so I guess this is what I need to talk about, and I want to, before we go back to the Desmos activity. So, based on that fundamental theorem of algebra, how many roots or how many zeros would f of x have?
3.
3 zeros. How many would g of x have?
5.
6? I'm on
7.
I was doing 5 and 2 and I was saying 7.
You just do the highest power. You don't add
So, when we say degree, what do we mean by degree?
the highest power.
Highest power, and I will say this, in standard form. It changes a little bit in factored form. We'll talk about why. But the highest power in standard form. So we've got 5 zeros here. How many zeros will h of x have?
4.
4 zeros.
Yeah.
How many zeros will y equals have?
Yeah, one.
Is that 1 to 7?
That's a 1. Remember that was that linear function. How many will k of x have? By the way, don't forget when I say zeros, I also mean roots. So how many would
1, 2, 3, 4, 5.
I am a little cold.
It is a little chilly. You will have 17.
so how many zeros would this f of x have?
17.
17. Why?
Because that's highest power.
The highest power, right?
17.
Yep.
Can you show them how it's possible?
Huh?
Draw, write 17 dots and show them how it's possible.
I mean, I wrote the equation, I have no clue what it would look like. So, please notice, like, this is only, again, this is only from an algebraic perspective. It's not from a graphical, it's not from a tabular perspective, but algebraically, these are functions with terms such that the base is a variable and the exponent is a whole number. And here's the thing, and this is what I want you to understand. That's off of the standard form. A better understanding of these polynomials, though, is off of the factored form. And that's what we're about to look at, and that's what we've been looking at, is the factored form. Remember, when we had two linear factors, it made what type of polynomial? What type of function?
Quadratic.
A quadratic, right? Because it had two zeros, right? When we go to three linear factors,
Cubic.
it's going to be cubic, because how many zeros are we going to have?
3.
3, okay? So, that's the standard form, but understanding it off of the factored form is a better understanding.
What 4 be a quadruple?
Like, what would the name of it be?
Yeah.
It'd be a quartic.
Oh,
If it's 4, it's quartic. You can also just call it a 4th degree, though. If it's 5, there's a name, quintic. You can just call it a 5th degree.
About 10 degrees, what would that be called?
10th degree. I don't think it has a special name. Alright. So all that being said, now when I introduce this third linear factor here, how many zeros do we have?
3.
Which is why it's going to be what type of function? Cubic. And so I want to point this out. I saw it's written somewhere. So I think Chelsea wrote this over here where she said a cubic has 3 roots, right? F of x, g of x, j of x, they each have 1 root because they're all linear. And so what did she say? She said ID, the roots are zeros.
Yes.
That's exactly what we did with the quadratics, wasn't it?
Yeah.
Okay. Determine the positive and negative factors. So let's look at it right here. So I've identified my zeros. I'm going to erase this. Here's my 0. Okay. To the left of here, the factors, are these positive or negative values? Positive. Are these positive or negative? Negative. Why do we know they're negative, by the way, for those who missed?
Under the x-axis.
Below the x-axis. Notice, literally, when I say the values, I'm looking at the y values. These are all negatives. So these are negative. What are these outputs? Negative. What do I get when I do a positive times a negative times a negative?
No, positive. Get a positive. Negative times negative is positive.
Okay, if you do like 20 2 times,
Next time,
negative 3, negative 6, you got 6 times. That negative, be positive, right?
Let's bring it back to this.
That's a
Hey. There is a quick and easy rule to know this. I'm going to point this out in a second. But right here, what's a negative times a negative? Positive. And so that would give me a positive times a positive, which is... Does anyone know the rule, though, to determine if it's going to be positive or negative? So, okay. Negative times negative is a positive. Negative times negative is...
negative.
That's going to end up being a positive. What is the pattern for when it'll be, so this will also end up being negative. What is the pattern for when we have positives versus negatives?
How is it gonna end up negative?
Positive.
So what? If it's an even number of negatives, what does it come out to be? If it's an odd number of negatives, it becomes a negative. Because here's the thing, right? Every 2, what's 2 negatives give me? Positive. So these two become positive. That's a positive. Over here, these two become a, and what's a positive times a negative?
negative.
These two become, and then 1 negative, so it'd be negative. So if it's an even number of negatives, it becomes positive. If it's an odd number of negatives, it becomes negative. But you can also just go every 2. You don't have to memorize that rule, but it does make things quicker.
So if I got 4 positive, 4 negative, I still got negative.
4 positives and 4 negatives. So, remember, every two negatives makes a what? So that's positive, this is positive, and then the rest are positives. So what is it? Positive. If it's an even number of negatives, it doesn't matter what how many positives. If it's an even number of negatives, it comes out to be positive when multiplying.
Right.
If it's an odd number of negatives, it becomes negative. So all that to say, I've got a positive times a negative times a negative, which comes out to be positive. And what are all these outputs right here?
Positive.
Positive. Now I want to look in between my zeros, just like we did with our quadratics, right? So notice I would start here at this x-intercept, I go to this one. When I look here, are these values positive or negative?
Well, you said where?
These green right here.
That's positive.
That's above the x-axis, so they're positive.
Yo,
What about these?
yo,
Remember, it's above the x-axis, right?
positive.
So they're positive. And then these are,
Negative.
and what's a positive times a negative times a negative?
Positive.
No, sorry, that's two positives and a negative. So that's negative. And what are these values down here? They're
Negative.
negative. It's just identifying if the factors have positive or negative values and then multiplying it. You don't have to have a perfect sketch, but you just need the right zeros and the right positives and negatives, and that's it. Okay? And so we're gonna get some practice with this in a second, but I wanna get this here first.
Oh, man. How do you get to write it down?
Well, you
Dude,
got
that's been up
YouTube.
there for forever.
You got YouTube though.
Number,
You got YouTube.
so we already actually did this. So it says on your vertical surface, sketch out your graph and explain why green cubic function has positive or negative values. That's what we just talked about. Here's what I want you to note now. Look at the graph up here or your iPads. I want you to talk with each other about what type of function is created by dilating a quadratic. So if we have a quadratic and we dilate it by a linear, what type of function is created? So talk about that with each other. If you start with a quadratic and you dilate by a linear, what do you end up with? So it's on the board, but also talk with each other.
Talk to the one. No problem.
Oh,
I'm coming, Dewan. Can I stop filming? Yeah, I guess I Yeah. I like being a recorder.
And maybe I should have done this originally, right? Right here, I took away the green h of x. I have a parabola, which is what type of function? Quadratic, okay? And then I'm dilating it, meaning I'm multiplying it by that black linear function. And so what type of function is that creating? A cubic. That's what we expect to see, a cubic, right? Okay? So when I look at h of x, is this in fact a cubic function? Amber, can you hit the lights for me, please? There we go. So how do we know, guys, how do we know that this right here is a cubic function?
Yeah, 3x.
3x squared. 3x intercepts. So, hey, chill. But I'm about to push back on this, so chill, okay? I'll go ahead and tell you this, and this is important, okay? It has three, what was the term you used before? It has three roots, it has three zeros. But did you know it's not always necessary to have three x-intercepts?
It can also be 3y.
Nope. Because if you have three y-intercepts, it's not a function. Listen, hey,
Listen.
right, okay. It's not always necessary to have 3x-intercepts. Because I want you to think about it. Have we ever seen a time when there are roots that are not x-intercepts?
All the time.
Uh-huh.
All the time.
Imaginary.
We've discovered imaginary roots and imaginary zeros, haven't we?
Oh, don't tell me to do it. They going with this too.
Yep, it always builds. Listen, so we're not going to do a ton of it, but we are going to do some. It's important to remember, that definition I gave for the fundamental theorem of algebra, did it say that it guarantees that many x-intercepts?
No.
Nope. But it's guaranteeing that many roots or zeros, okay? So, when I talk about a quadratic, first off, I want you to look at this. There's an equation tied into this. It is f of x equals 0.4 times x minus 2 times x plus 4. And we should see that. Do we see a 0 at negative 4?
Yeah.
Yeah? Do we see a 0 at 2?
Yeah.
Yep. And what are we doing to that quadratic? We are dilating it by the linear, right? That black linear, which is
JX equals
1x plus 1.3. And so yes ma'am. Right here. So remember, it's x minus r1, right? X minus r2. So remember how it's always the opposite? Yeah. So it was, can you let Kamaya in, please? So it was a positive 2. It was a positive 2, so it's x minus 2. It was a negative 4, so it's x plus 4. Right? So it's the opposite there. Thank you. And so, remember, this is the dilate part. We're multiplying. But we can now clearly see, when I take a quadratic, how many roots does every quadratic have? 2, right? Every quadratic has 2 roots. Every linear has 1 root, so how many total roots do I have? 3. So when I take a quadratic that has 2 roots, and I multiply it by a linear that has 1 root, how many total roots do I have? 3. Remember, the whole idea of dilating is creating new zeros. So we're creating those new zeros when we dilate by a new polynomial. And so how do we determine, and so I'm going to give you all practice with this in a second, but how can you determine what the dilated function looks like using the graphs of the factors? So if I did not have, that's not what I need to do, hold on. So let's say I don't have h of x. Let's say I change this function. How'd that happen? Okay. So now I have a completely new function. Alright, so what I'm trying to do, it's going to get interesting. Dewan, can you hit the lights since you're not in your desk? Thank you, sir. So, now I have what type of, I still have a quadratic, and what am I doing to it?
Move it.
Dilating it by a linear. So I should get a cubic. And what I want to know is, what is that cubic going to look like? This equation that I have right now is, actually this is h of x, is negative 1 times x plus 1.5 times x plus 4.
And somebody tell y'all, I think. That's how I think.
Times negative 2x plus 4.
You can take it someone.
I haven't even done anything. So, listen. When I look at this h of x right here, does anyone know what this looks like off the top of their heads?
Back to form?
No, like, what does it look like on a graph?
Oh.
A double parabola.
Well, that may be the quadratic, but I'm talking about h of x. I'm talking about this whole thing. I don't know what that looks like.
It looks like a quadratic.
Okay?
Quadratic plus linear equals cubic.
Because I'm about to make sure that we know how to get it. Okay, listen. What I'm saying is, if I don't have this graph here, I just look at that equation. I don't know fully what it looks like. I can figure it out, but I can't just look at that and know. When I look at this parabola, I know concave down, I know an x-intercept of negative 1.5 and negative 4. When I look at this linear, I know it has a y-intercept of 4 and a slope of negative 2. But when I get to cubics and quartics and quintics and higher degree polynomials, I don't know what it looks like off the top of my head. However, I know that h of x is going to have the same exact zeros. So I mark my zeros. I know that those are going to be the zeros of h of x. And I mark it off with these dashed lines. Okay? Then I can figure out what it looks like by looking here at the left. Now, I need you to pay attention. How many factors do we have?
3.
Kind of 3, but remember, we really have a quadratic and a linear. So I'm just going to focus on this quadratic right here. What is my h of x going to look like over here?
A down pull right here.
Why negative? Now you're talking about this piece, right? That these are down? But how many factors do I have?
3.
You got 2 right now.
Remember, I got a
2 negative times a positive.
I got a quadratic and a linear. Aren't you only referring to this quadratic right here? What's the linear going to be though? Is it positive or negative?
Positive.
So the quadratic here is negative. The linear is what? How do you know it's positive?
We don't know.
You do know. So remember, is this line going to stop
They're on the
here?
right side. No.
It never stops, so it's going to keep going up, right? All the way up here. Yes, I know I'm short, but what are these y values going to be? Are they positive or negative?
Positive.
Positive. Okay. So guys, even though it looks like it stops here, it keeps going. So I know that those outputs, Taj, are going to be positive. And what's a negative times a positive?
We're talking positive.
So whatever, I don't know the exact values, but I know h of x to the left here is going to be negative. Notice how I had to go to that x-intercept, right? Now I'm going to look in between here. Okay? Looking in between here, the quadratic, positive or negative. The linear is going to be, and what's a positive times a positive? So these are all going to be positive. And it's got to get back to the 0.
It's going to be negative.
How do you know?
It's going to be negative.
So notice this is negative, isn't it? The quadratic has negative values, and the linear has positive values. So it's going to become negative, and it's got to turn back up. Okay? Remember, it's got to get to that next 0. And then when I look to the right over here, why is it going to be positive?
What's going up?
But how do you know it's going to go up?
I mean, it can just stop and go back down, can it? I mean, can it
By looking
stop
here,
Can it
I
stop
got to
back down?
actually look at the factor. These values are what?
Can it,
Negative.
can it slant back down?
Hey guys, that's my linear factor, isn't it?
Yeah.
Have you considered your quadratic factor?
No.
Is the quadratic going to be positive or negative? It's going to be negative. And a negative times a negative is? So remember, and I need you to pay attention to this. Please note, how many factors did we have? We had a quadratic and a linear, so we had how many factors? So remember, we wrote it as 2 here, but this was a quadratic, right? So, Addison, let's look at it this way. Originally, how many graphs did you have? 1? Sorry. How many graphs did you originally have?
2. Okay.
1? 2. So, I may have written this in factored form, but how many factors did I actually have? How many parabolas, or how many graphs did I have? 2. So, notice, how many positives or negatives did I always multiply? 1. There's 2 factors. I always need 2 factors to multiply. Okay. So,
Now that we found the graph out.
now that we found the graph out, let's check to see if we're close. Can you hit the last wrinkle one?
We close.
It's humongous.
I was saying, oh yeah, it's,
Touch.
so look. Ooh. So we couldn't see it all, but notice it has the right negatives and positives. What I want you to do at this point is I need you to go to your vertical surfaces, and I need you to work on sketching, attempting what these functions are going to look like. Now, hear me clearly on this. To make your life easy, I'm not asking you to do this entire grid.
Hold on.
Hey,
I just slide that. I see it slide.
Go on. Next time I hear that music, I will be collecting those beats. Is that clear?
I don't got the one. I don't want me.
The one ain't even got nothing to connect to them.
That's what I'm
You got them
saying.
on.
I ain't even got no something to worry.
I watched you touch the headphones to pause it.
He just got it for style,
Oh, what
Mr.
is he talking about?
He just got it for style.
Press.
Like, calm it down.
He said, oh, no.
So, all that you have to do to make your life easy is this. This x-intercept is negative, this y-intercept is negative. Just do a quick sketch of the line. This y-intercept for the green function is negative, the x-intercept is positive. And so they actually share, so boom. And then, so when you're doing this at your vertical surface and you want to sketch it, you can do it this way. And then the last one here. So it just needs to be close on the lines. You can sketch the function from there. You just need to be able to tell the zeros, the positive, and the negative. What you can also do if you want is you can actually take your iPad and you can mark it on your iPad and not go to the vertical surfaces. I don't care what you do, but I need you to sketch a function and be able to justify why it looks like that. So I need you to work on the 3 linear factors, then I need you to work on the quadratic and the linear. So actively talk and collaborate, make sure that everyone agrees with the way it looks. So let's get up, let's work with our small group. The one that you were going down for.
I'm trying to do something.
I need you to explain to me how you got that.
I mean, down there.
So what I'm gonna do,
Okay, we go to
You
my
can use the
hair.
iPad.
I want something like this.
But how, let me ask you, how do you know for sure?
we're trying to see if we can grab
I'm a paying customer, you can't deny.
these.
How do you know for sure that those are
You
negative?
gotta pay for me. We just.
You just
We
So it looks like you are here. Is that what you did here?
I don't have no wig. I'm not a wig wearer.
Please post it, there's like a pitting.
Yes.
He said
I
press.
need you to actually
Why?
think about that.
I don't really.
There she go.
Guys, I need to get
I don't know.
So,
We have it, we have it pulled up. We should be on slide 5. Yeah. So starting with that left graph, see if you can practice graphing the resulting function. Product of those factors.
Yeah, Mark, I don't even know if I can do. No, we can draw them.
Yeah, you can draw it, or you can go to right here. Either one you want.
I was gonna do it on my day.
Sure, you can draw it.
Well, Mark, where did that boy go? Back there? Okay, that doesn't look like the work. Okay. Okay. You should do tomorrow, don't we didn't even get it. One of my papers like.
I press the second.
What up, dog?
Come on, you go.
You can't do it. His group ain't there.
There's 4 people in that group.
Press the, aren't you? Can we talk about this?
Brady,
Come on, the red thing?
you and the watch need to work together. Come on, do it. Do either of y'all have an idea?
Preston, his iPad is right here.
Mine's dead.
I just yeah, right?
Oh, what you put in there for? You ain't going to.
Even though.
Right, it's not that sharp. If you're having trouble because we don't have an iPad, then you can ask permission.
Oh, so we don't worry too much about like the
We've
exact
already
axes and all that on points. Just do
Unless
it
we've
with
been sent
sketch.
to ask for it.
Don't worry about your specific.
But you just leaving your group is not a. If you have
Can we go down
issues
first?
with no iPad, you let me know and I'll.
How do you know to go down first?
Is that clear?
So it's So when you say going down, you mean going like this? Here, draw what you're referring to. Draw what you're talking about.
Brady, you can work with them.
Wait, we're not doing
Wait, are you supposed to be in the eights?
So there's a couple ways that we can. So I like the general shape you got, right? We got that the shape of a cube.
I was thinking about like, why?
Now, we learn about some specific processes to refine it. So, for example, what points do we know should always be on our function?
But you're not supposed to go there. Y'all are supposed to work.
Where is it gonna cross the x-axis? Yeah.
No, Brady, no.
Yeah. Go ahead and label it.
Okay,
No.
this is what I did.
If you're supposed to be working with
So, are we all catching along?
unless you are going to ask questions to learn from.
Yeah, we can't really do it.
If you don't have an iPad, that's not the rule. So you need to ask permission to change things.
That's better. So don't worry about drawing that part yet. Just go ahead and label those points first. And then we got a process for determining what ranges, what intervals would be positive and negative. Talk with your group. And also, what I like to do is and now ask yourself, what do we do to determine values between vertical dash lines? How are we doing there? So, I'm trying to learn. Super quick graph. Not worrying too much about the exact value at all. There's one. There's another one.
What?
They're not color coded, but generally this one is already.
No.
Okay. So one thing not.
You work with your group, unless space you go ask questions, so you can go back to your local. And that's not what you're talking about. Okay.
So, what can we say to construct the results?
Can I go to a different time? That was it.
So notice.
So, ladies and gentlemen, I want to wrap this up. At least look at this one right here before we leave. Mr. Kim, if I can grab their attention. Aces all the way over here, Jamie. If you can face this direction, please. Okay. So, what points do I know? By the way, what type of function am I going to get right here? A cubic. What degree is a cubic? I know it's going to be third degree because it has how many zeros? 3. What points do I know my cubic function will have? It's going to have what? 2 negatives. -4. Back up. You didn't answer my question. I asked what points do I know my cubic will have? The same roots, the same x-intercepts. And there's only a few options. Hey guys, I'm tired of packing because I could be done in about 5 seconds, not literally, but close. But because we are packing, you're not getting this information, Tyler. Kamaya, you're not getting this information. Huh? But I need you looking at the thing I'm about to do to make sure we understand this. When I look over here, remember, you don't have to, but I highly suggest you mark that x-intercept with vertical line. Now I know I'm only looking to the left. So when I look to the left, are these values down here or are they up here?
Down there. Down there.
Say that one more time. A negative times a negative times a positive. Remember, how many factors are there? 3. How many negatives do I have?
2.
So this needs to be positive. So when I look in between here, what do I have? I had 3 negatives, which means it's going to be negative. Got to come back to my 0. And that's what I want us to pay attention to. I got a positive, a negative, and a negative. So what's it going to be? Positive. And then I'll go ahead and confirm here. Tomorrow, we're actually going to look to see when it doesn't actually go all the way through every time. Now, Maddie, be careful. You're close. But did you actually go through that 0? Guys, you got to make sure you go through the zeros.
Good. So I guess I'll never see you again.
So make sure you go through those zeros. And let's make sure we have our iPads tomorrow, please. Tired of groups having to go elsewhere because they don't have their iPads.
I've been done with my hours. Oh, come here.
Oh, Mr. Hobby. We never made copies, did we?
No, we didn't.